In Chapter 9, we're going to be focusing on counting and probability, which are two of the major components of a branch of mathematics called combinatorics. So we've all heard the phrase, or even said, what are the chances of XYZ happening where XYZ is some event? And like I said, of course, in here in the notes, of course, that means we have a branch of mathematics focused on probability, and that branch is called combinatorics. So in this chapter, we're going to be learning about several of the larger topics from combinatorics and how we can apply them to situations in our everyday lives. So I asked you to watch a video on using the coin flipper in your calculator, or I said you could use random.org. Either way, you could use either one, and we're going to use the results here to look at our first foray into probability. So I said we wanted to flip two unweighted coins simultaneously. And when we say unweighted, that means that you have a likely chance of both heads and tails happening is equal. They are called equally likely events. If we weighted them, then it would be a weighted coin, which would mean that the probability of flipping a head would, if that was the side that was weighted, would be higher, right? If we weighted it for heads, then the probability of heads would be higher. If we weighted it for tails, then the probability of tails would be higher. So we're focusing on two unweighted coins, and we want to flip them simultaneously and observe our outcomes. And those outcomes include 0, 1, or 2 heads. And you might hypothesize that the chance of obtaining each outcome is about a third. So when we flip two coins, maybe a third of the time we get no heads, a third we get one head, and a third we get both heads. But we're going to test that out. So I did this with a video that I showed you guys on using the TI-84 probability simulator. In the PDF, I also have it linked to that video on my YouTube, so you can certainly also click on that. So what happened was when I used the TI-84, I ended up finding that I got, let's see here, I think I had seven instances of 0 heads. I had 29, so we can pretend that I actually was doing this while we were looking here. So what you would do was use this part of the table to mark your tally marks for how often it happens. And I had 29 instances where I flipped just one head, and then I had 14 instances where I flipped both coins that were when they were flipped were ahead. So I had a total of 50 flips. So I flipped my coin 50 times. So we had a total of 50 coin flips. Okay? And what happens is then our frequency is how often does our event occur. So our events here are that we get 0 heads, we get 1 head, or we get 2 head. And we counted up how many times each one happened, and that's called our frequency. So this is the number of times an event occurred. And our relative frequency is the proportion of times. So the total proportion for each event. So how many times did it happen out of the total number of events? So for 0 heads, we would have 7 out of 50. For 29 heads, we'd have 29 out of 50. And for 14 heads, we'd have 14 out of 50. And if we look at each of these as a proportion, which would be a decimal between 0 and 1, we get 0.14, or 14% of the time. Or for 0 heads, we got 58% of the time, or 0.58 was our proportion of outcomes that was 1 heads. And the last one would be what proportion of the outcomes was 2 heads. Well, that was 14 out of 50, which is 0.28, or 28%. Now, ideally, that relative frequency there would add up to just about 1. Sometimes it ends up being like 0.999 or 1.01, but it should be roughly 1. A lot of times where it doesn't add up to a total of exactly 1 means that we just add a little bit of rounding. So what happens is we notice that we don't have 1/3, 1/3, and 1/3. In fact, not really even all that close. 2 heads is maybe closer to 1/3. Maybe 1 heads is closer to 2/3. But then what about this 0.14 of our 0 heads? So maybe not quite what we thought it was going to be. So should we have expected this? Well, let's talk a little bit about some probability theory. So probability measures the number of desired outcomes compared to the total number of outcomes. So the total number of expected outcomes is called the sample space S. And we can define the probability of an event E by saying that the probability of E is the number of possible outcomes in event E divided by the number of possible outcomes in a sample space S. So remember, P means probability, N means number. So the probability of event E occurring is equal to the number of possible outcomes in event E divided by the number of possible outcomes in the entire sample space. So how many ways can event E happen over how many ways can anything happen? Right? That's the idea here. So how does this change? And I said no pun intended because we're flipping coins, which we also call change. How does it change our expectation of the outcome of flipping 2 coins and observing the number of heads? Well, let's think about it this way. Let's define our sample space S. So all possible outcomes. That is our sample space S. And I had to put those little serifs on S because otherwise they turn S's into 5s. You don't have to put the serifs on S. That's okay. I do it just so I don't accidentally turn it into a number. So our possible outcomes for all possibilities for flipping our 2 coins is that we could have 2 heads. The first could be a head, the second a tail. The first one a tail and the second a head, and they both could be tails. Oops, that looks like pie. Let me try that one more time. I made it look like pie, sorry. I think I've been teaching too much calculus lately. There we go. So that's our sample space. So in this case, the number of ways that we can flip 2 heads is only 1 way. Number of ways we can flip 1 head, well, we have 2 of those, don't we? We have 1 head here and 1 head here. So we actually have 2 ways. A number of ways we can flip 0 heads, which means all tails, is just 1. So what that means is the probability of 1 head would be the number of 1 head divided by the number of events in our sample space. So we would get 2 out of a total of, we'll count them up, 1, 2, 3, 4. So S, it has cardinality 4. So it has a size of 4. So our probability of just getting 1 head is actually 1/2. If we looked at the probability of no heads, well, there's only one way to do that one, right? That's when we get both tails. So we just get 1 out of 4. And this is going to be the same for the probability of both heads. There's only one way out of 4. So that changes a little bit, maybe what we think we should have gotten. So let's see if that matches with what we found when we plugged it into our calculator. Well, for 0 heads, we think it should be about 1/4. Well, it's a little low. But again, this is because we have a sample size of only 50. And if you've never taken statistics, then I can explain this to you a little bit more. It's the nature of randomness. So what happens is we have something called the law of large numbers, which says then as we get a larger and larger sample size here, so if we did 5,000 coin flips instead of 50, we should see these numbers get closer and closer to the numbers that we expect down here, that our theory tells us they should be. So we were just a little off, a little under here on 0 heads. We were just about right for 2 heads and 1 head. But because these ones are a little bit higher than they should have been, this one was a little bit lower. And as a reminder, all probability should be between 0 and 1. This is because we're talking about the proportion. So you can't have a piece of a whole that is bigger than the entire object, right? You can only go from no part of it to all of it. If we looked at them as percentages, this is between the probabilities between 0% and 100%. In probability, there's no such thing as 110%. There's no such thing as a negative percent. Only between 0 and 1. Yes, it can be 0. Yes, it can be 1. A sure event is 100%. An impossible event is 0%. So we do have those possibilities. That's why our probability is between 0 and 1 and includes 0 and 1. Let's switch from coins to dice. So let's try a problem where we're going to roll 2 six-sided unweighted dice. Six-sided dice are our standard dice. There are, yes, other kinds of dice, and in my face-to-face classes, this is where I really enjoy bringing out. We have a container of all kinds of different sided dice. We have 4-sided up through 20-sided dice, and we can roll them and play with them and try out their different probabilities, see if we can approach what we think it should be. So for this case, though, we're just going to assume we have our normal 6-sided dice. So we want to list the sample space of all of the equally likely outcomes. So our sample space here is going to be the set of all possible outcomes. Well, we could roll a 1 and a 1, or a 1 and a 2, or a 1 and a 3, a 1 and a 4, a 1 and a 5, or a 1 and a 6. Ooh, that's a lot. Now we can repeat this with 2, 3, 4, 5, 6, all the way out to 6, 6. So I'm going to ask you to take a moment to pause here and finish it out, and then come back and we will have it loaded in. Now that you've taken the time to write out all of the events in our sample space, let's see how many events we actually have here. Well, we have 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. So we have a total of, so we know we have a total of 36 possible events in S. In other words, N of S is 36. We might need that soon. So if we let E be the event that we roll a sum of 7, what is our sample space? Well, think of all the ways we can roll a 7. We could roll 1 and 6, 2 and 5, or 3 and 4 in any order. So we have 1 and 6, and 6 and 1. 2 and 5, 5 and 2. 3 and 4, 4 and 3. That is a sum of exactly 7. So how many ways can we find it? Well, there are 6 ways. And those 6 are our sample space of E. So E is the set of those 6 combinations. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So there are 6 ways. So if we wanted to find the probability of event E happening, then we know that the probability of E is equal to the number of ways that E could occur divided by the number of ways our sample space could occur. So if we look at E, we literally only had 6 possibilities. So our probability would be 6 out of our sample space size, which is 36, or 1 in 6. So our solution here would just be 1 in 6. But what if I asked you to find the probability of not rolling a sum of 7? Then that would mean we'd have something called the complement. So the complement is the exact opposite. It's everything else in the sample set that we don't want. So if I wanted a sum of 7, all of the events that would be in the complement of that event would be all of the rolls of our dice that do not have a sum of 7. So what we can do is use this complement to our advantage here. So we have that the probability of E complement is 1 minus the probability of E. So we would say that the probability here of E's complement would be 1 minus the probability of E. So let's define what exactly this means. Well, E complement is the set of all sums in our sample space that are not 7. So what that means is I have then the probability of not rolling a sum of 7 is 1 minus the probability of rolling a 7, which is 1/6. So our probability of not rolling a sum of 7 is 5/6. Oftentimes, the other way we think about it is if 6 out of my 36 possibilities give me a sum of 7, then 30 of them do not. And those 30 out of the 36 would give us our 5/6. That probability would reduce to 5/6. Where things can get a little bit interesting with probability is when we now switch over to something like find the probability of rolling a sum that is at least 7. So if we scroll back up to our sample space, well, the 6 that we have marked are already 7, and 6 and 2 is at least 7, that's 8. Well, so it would be 2 and 6 and 6 and 2. Well, so we have 5 and 3 and 3 and 5 and 4 and 4. 6 and 3 and 4 and 5 are all 9, so those count. 6, 4, and 5, 5 are 10, and 6 and 5 are 11, and 6 and 6 are 12. So let's see how many that makes us. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 ways to roll at least 7, a sum of at least 7. So if we scroll back down to E, we would say then that our number of ways, so this event is going to say, roll a sum that is greater than or equal to 7. And the number of ways we can do that, we just counted up, is 21. So our probability of this event occurring is 21 out of 36. They're both a multiple of 3, so you can reduce it down to 7/12. And that is our probability of rolling the dice and getting a sum that is at least 7. So where silly things like these can come in handy is you could start trying to Convince your friends that you can make a game out of rolling dice where you always win. If you tell them you're going to get a sum that's at least 7, you would be right 7 out of 12 times. A little better than half. So F asks us to find the probability of rolling a sum that is less than 7. So that means our complement here is we have a sum that is less than 7. And we remember from our negations from back in chapter 2 that if we have greater than or equal, its negation is less. And that's exactly what we have here. So the probability, remember we just saw it above, the probability of our complement is equal to 1 minus the probability of our event. So the probability of E complement is 1 minus 7 over 12, or 5 over 12. So 5 out of 12 times, you'll roll a sum that is less than 7, but 7 out of 12 times, you'll roll a sum that is at least 7. Much like we have had rules for simplification within sets, simplification within logic, simplification within Booleans, we also have some rules for simplification and computation with probability. So the first rule I wanted to look at is the multiplication rule, which says suppose an operation can be broken into k successive ordered stages with n1 different outcomes in the first stage and 2 different outcomes in the second stage, all the way up through n sub k different outcomes for the kth stage. Then the total operation has n1 times n2 times all the way out to n sub k outcomes. How does this work? In other words, anytime you have an and, if you hear the word and, you're going to multiply. Multiply your probabilities. Oops, probabilities. There we go. So a couple wants to have at least one boy and one girl when they start their family, and they will stop having children once they do. Also, they agreed to have no more than 3 children. What is the probability the couple will have 3 children? So that means we have to have girl and then boy. That is the only way that they're going to have the 3 children. Because if they get or they could have a boy, and a girl. Those are our only 2 options here. Because otherwise, if they get a girl and a boy, they're done. But wait, there's more. They could get a girl, and a girl. Or they could get a boy and a boy and a boy. Okay, hopefully your head doesn't hurt too badly so far, because I have a way to help you out here. This is something that we can use to visualize probability, and it's called a tree. So sometimes we need something to help us visualize all the different possibilities within one of our probability problems. So I said here that this problem is not as easy to describe as the previous examples with the dice and the coins, so we're going to use our tool called a tree diagram to help us visualize. So the way we think about it is we have the 2 parents. They could have a girl or they could have a boy. Their chances of either one happening, that probability, if we look at this step, right, this is step 1. So this is k equals 1 is just girl and boy. So their opportunities here to have each are half. The probability of having a girl would be half. Probability of having a boy would be half. From there, if they had a girl first, they could have a girl or a boy. Again, only 2 options. So a 1 in 2 chance of having a girl or a boy again. We come back down here to girl and we have the chance of having another girl or a boy. So we have a 1 in 2 chance again. Notice, however, here we don't split this boy into girl and boy again. That's because our parents had a girl and then a boy, which means stop. That's what they wanted. We'll notice down here that if we have a boy first and then we have a girl here, then they also stop. Their chances of having a girl after a boy are 1 and 2, a boy after boy also 1 and 2. And then again, after that second boy, they still have half and half. I will say in reality, it's really probably not half and half. A lot of that is genetics at play, and there is sort of a going theory that once you have more than one of the same, you end up getting more of that one if you keep having kids. My family kind of holds true to that. My sister has 5 boys. I have 4 girls. So chances are if we'd kept going, we probably would have had more girls. We might have had a boy in there somewhere, but we are perfectly content with our 4 girls. My sister is perfectly content with her 5 boys. So this family was just hoping to get one of each at least. So let's see what happens then if we can describe each of these possible outcomes. So if we follow our tree through its first set of branches, its outermost branches, let's go from the parents to a girl, and to another girl. In other words, my family, before our last child. So we would have our possibility here would be girl, girl, and then a girl. So that outcome would be girl, girl, girl. And the probability here of having girl, girl, girl would be the probability that we had a girl to begin with, which is 1/2, and we had another girl, which is another 1/2, and we had another girl, which is 1/2. So it is 1/2 times 1/2 times 1/2 for a total of 1 out of 8. We can repeat this now with branching the next branch down. So we could look at having a girl, and then a girl, and then a boy. So we have a girl, and a boy. And the probability of that girl, a girl, and then a boy, well, follow the tree, follow that branch. 1/2, 1/2, 1/2. It's the same. Well, maybe they'll all be the same. They have a 1 in 8 chance of having all girls, a 1 in 8 chance of having 2 girls and then a boy. So then we look at the next branch is, oh, I forgot to circle that we did this one. Our next branch is that we go from the parents to have a girl and then a boy. And then they stop. So it's just girl and then a boy. And the probability of a girl and then a boy is just 1/2 times 1/2, or 1/4. Interesting. That's not the same probability as the other two. Well, if we follow the same path, on the bottom, we find out that we could have a boy and then a girl. And that probability of boy and girl would be 1/2 times 1/2, which is 1/4. Then we could do boy, boy, girl. And the probability of having a boy, and a girl would be 1/2, 1/2, and 1/2, or 1/8. And then our last opportunity here, a boy, and a boy, just like my sister. And that probability is going to be 1/2 times 1/2 times 1/2, or 1/8. So this is a tree diagram, and we've labeled all of our different probabilities that go with each branch. So now that we've calculated all of the different possibilities, there are 6 possibilities here for how this could pan out for this set of parents, and they have 6 outcomes. Are they all equally likely? And and then if we look at it, we see that the chances are not equally likely because The probability of getting a girl, then a boy, or a boy, then a girl is 1 in 4. But the probability of getting, oops, let me find, there's my thing, of getting 3 girls is 1/8, 2 girls and a boy is 1/8, 2 boys and a girl is 1/8, and 3 boys is 1/8. So they are not all equally likely. So the outcomes are not equally likely. Part B says, let's scroll up there. Is it equally likely that the couple will have 2 children or 3 children? Well, let's see if we can figure it out. The probability that they will have 2 children. Well, how many ways could they have 2 children? Well, that happens only when they get the probability of a girl and a boy plus the probability of a boy and a girl. And we'll talk a little bit more in a moment about why this is adding and not more multiplication. So we end up here with 1/4 plus 1/4, or 2/4, which is 1/2. So they have a 1 in 2 chance of having 2 children. But they have 4 ways to have 3 children. So the probability of having 3 children could be, let's see, the probability of having a girl, and a girl, or let's see here, we could have a girl, and a boy, or a boy, and a girl, or a boy, and a boy. And what happens is each of these is 1/8. So we end up with 1/8 plus 1/8 plus 1/8 plus 1/8, or 4/8, which is 1/2. So interestingly, they do have an equally likely outcome for 2 versus 3 children. So the couple is equally likely to have 2 or 3 children. Isn't that interesting? So what is the probability then of the couple having more girls than boys? Well, let's look at our tree. And in which cases do we see more girls than boys? Well, let's see here. Girl, girl, girl. Yep, that's one of them. Girl, girl, boy. Sure is. Girl and boy, that's the same number. Boy and girl, same number. Boy, boy, girl. Boys outnumber the girl, and boy, boy, boy. There aren't even any girls in that one. So in this case, we would end up saying, well, there's only 2 ways to have more girls than boys. And each of those has the probability of 1/8. So the probability of having more girls than boys means that we need to define our event. So our event E is that the couple has more girls than boys. We already said the number of ways this event can occur is 2. And we said the probability for that event then would be the probability of getting a girl, and a girl, plus the probability of getting a girl, and a boy. Those were our 2 events. So we end up with 1/8 plus 1/8, which is 2/8, or 1/4. This tree diagram problem, I have to say, is probably one of my favorite problems that I've come up with. And I use this when I teach statistics as well. My children don't seem to appreciate this problem quite so much. And I will say that last fall, I had a student who was a tutor, and 2 of my daughters were also tutors. And so he picked up on the fact that it was about my kids, and that's how he realized that 2 of the tutors were my kids. And so when he saw them when they were tutoring, he said, "Oh my gosh, your mom did this problem." And they go, "I know, the dishwasher problem." So they thought it was kind of funny, but they would appreciate if I would give them a little more credit for filling the dishwasher, apparently. So let's see what they're talking about here. I said that Professor Noyes has four daughters and they are required to do chores. One of their chores is loading the dishwasher. The eldest daughter is off to college, so she loads the dishwasher 0% of the time. The second daughter, Kay, loads the dishwasher 25% of the time, and she remembers to actually start the dishwasher for 43% of her loads. Professor Noy's third daughter, N, loads the dishwasher 35% of the time, and she is much better at remembering to run it. N starts the dishwasher for 90% of her loads. This is probably still true, honestly. The youngest, A, is responsible for the remaining 40% of the dishwasher loads, and she remembers to run the dishwasher about 77% of the times she loads. So I want you to draw a tree diagram for all of the possibilities here of our different events occurring and label all of our branches and their probabilities. So what I'm going to say is we're going to start with my kids first here. So it will branch off to K and N. So we're going to have, let's see if I can line these up all right. K, N, and A. Okay. And it even says here that the eldest daughter is gone, so she's 0%, she's not there. So K loads the dishwasher 25% of the time. So this is 0.25. And we'll put it in a different color here. There, we'll do 0.25. Let's see here. So we checked off this one. Let's see here. N is 35%, so 0.35. And A is 40%. So she's 0.4. From here, you want to look at the probability that if K loaded it, it was run or not run. When N loads it, what is probability it's run versus not run? And A, run and not run. So each of these branches will also branch into two more. So I would like for you to pause here and see if you can finish drawing your tree here. Because on, say, an exam, if I give you a tree diagram to draw, you want to be able to draw it in yourself. Hopefully you've taken the time to finish drawing the rest of your branches. So this is where we need to determine which probabilities are now labeled on each branch. So if we look back at K, it said that she loads the dishwasher 25% of the time and she remembers to run it 43%. So that's our 0.43, which means the probability that she doesn't, or the rest of the time she doesn't remember to run it, is going to be 57%, or 0.57. For N loads it 35% of the time and remembers for 90% of her loads. So 90% here, which means only for 10% does she not remember. So our probability that she ran it would be 0.9. Our probability that she did not run it would be 0.1. And for the last one, for A, it says that she remembers 77% of the time. So her probability for running is 0.77, which means her probability for not running is 0.23. So we can now look at the different probabilities that we get from our outcome. So if we do, let's see here, maybe we'll do K and run. We could do K and not run, N and run, N and not run, A and run, and A and not run. Those are our different possible outcomes. So let's see here, our probability that that K loaded and ran it would be 0.25 times 0.43. Probability that K loaded it and didn't run it, so not run, would be 0.25 times 0.57. So again, we're just going branch to branch, branch to branch. Now let's do N. N loads 0.35, running is 0.9. So the probability of N loading and running is 0.35 times 0.9. Probability of N loading and not running is 0.35 times just 0.10. Probability of A loading and running would be 0.40 for loading and 0.77 for running. And the probability of A loading and not running would be 0.4 and 0.23. So if we multiply each of these out, we can get a decimal representation for each probability. So the probability that K loaded and ran the dishwasher is 0.1075. The probability that K loaded and did not run the dishwasher is 0.1425. The probability that N loaded and ran the dishwasher is 0.315. The probability that N loaded the dishwasher and did not run it is only 0.035. Probability that A loaded and ran it is 0.308. The probability that A loaded but did not run it was 0.092. So there are all of our probabilities listed in a tree form, and then we listed them all out by its respective branch. So if I open the dishwasher and find it full without being run, what is the probability that K loaded the dishwasher? Well, you might think, okay, then that's just this, K loaded and didn't run, this 0.1425. But it's not that simple, because there are other people who could have loaded the dishwasher. It is loaded, but it wasn't run. So the way that we could have had the dishwasher loaded and not run is our total sample space in this case. So here we would end up with, let me drag this up just a little bit. Okay, so we would have here a probability of K and not run, right? K and not run is going to be divided by the probability of just not run. And there are several different ways the dishwasher could be not run. Well, here's a not run, here's a not run, and here's a not run. So our probability of our event happening here is going to be the probability that K loaded and did not run it is 0.1425 from our chart. But the different ways the dishwasher could be loaded and not run is that it could have been K who did it, or it could have been N who did it, or it could have been A that did it. So it turns out that it's not quite as simple as we might have thought. But here we end up with 0.1425 divided by 0.2695, or 0.5288. And I will tell you, this is a topic we're going to get to a little bit later called conditional probability. And so we'll hear about this again later. I'm not writing it in those terms. I'm simply just calling this our event, is that it was loaded but not run. In very similar ways here, we're going to look at problem C, which says if Mr. Noyes opens the dishwasher looking for a clean fork and he finds it full of clean dishes, what is the probability that A loaded? This is very similar in that we're going to do the probability that A loaded and ran the dishes divided by the number of ways the probability that the dishwasher could have been loaded and run. So for this one, we have a new event, and the probability of that event is going to be the probability that A loaded and ran it divided by the probability that it was run. So the probability that A ran it was 0.308. And the different ways it could have been run could have been that A loaded it and ran it, or N could have loaded it and ran it, which is 0.315, or K could have loaded it and run it, which is 0.1075. So we end up finding out that we really get 0.308 divided by 0.7305. And I will say it's a pretty good indicator that at least 73% of the time, the dishwasher gets run after it's been loaded. So that's probably a good thing. So we end up here then with 0.4216. Or there's a 42% chance that A loaded and ran the dishwasher. For D, we're going to look at a little differently. Let's see here. If the eldest daughter comes home from college, opens the dishwasher, and finds a clean bowl, she finds the dishwasher then full of clean dishes, what is the probability that N loaded it? So it's not really all that different. It's just now instead of looking at K or looking at A, we're looking at N. So our probability of this event is going to be the probability that N loaded and ran the dishwasher divided by the probability that the dishwasher was run. So we already know that sample space in the denominator here. We just did it. But our probability in the numerator is that 0.315 for N and running. And that's going to be divided by the same sample space before probability that it was run, which was that, and I'll even put it in purple, 0.7305. So this probability that the dishwasher was loaded and run, if it was N, that would be 0.4312. So we end up finding out that if the dishwasher is loaded and run, there is a 42% chance that A loaded it and ran it, and there's a 43% chance that N loaded it and ran it. Doesn't say a whole lot of good stuff for K, which is why, who was one of my tutors at the college, that's why she thought, hey, you kind of threw me under the bus here. In reality, though, she probably really didn't load the dishwasher that much because she was busy at the time in high school. But I thought it would be fun to do a probability problem based on a sort of real life situation in my house. For example, 9.2.3, I get to pretend that I own a bank. So what I said here is that the Noyes National Credit Union issues debit cards to its members that use a 4-digit PIN number. So how many possible PIN numbers are there for each debit card? Well, if you think about it, we have 4 slots for our pin. So 1, 2, 3, 4. And how many ways can I choose the first number? Well, it can be any single digit. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, which is 10 ways. Well, I haven't put any limitations on it, so you could also choose any number for the second digit, and the third, and the fourth. So each digit has 10 ways it could be chosen. If you want your pin to be 1111, you got it. If you want your pin to be 1234, you got it. If you want your pin to be 9999, you got it. There are no limitations. So how many possible pin numbers are there? Well, that would be 10 times 10 times 10 times 10, because we want the first and the second and the third and the fourth. So we end up having 10 times 10 times 10 times 10, because remember, and means multiply. And I know we've sort of glossed over this a little bit here, but we remember that or means adding. So here, though, we have 10 times 10 times 10 times 10 because we have to have all of them. It's not, it could be 1 or 2 or 3 or 4 digits. It has to be 4 digits. So you have to pick one for digit 1 and digit 2 and digit 3 and digit 4. So we have 10 to the 4th ways to pick our pin number. So that would be 10,000 different pin numbers to choose from here. It's a lot of pin numbers. How does that change if I have to make the first one a 0? So I'm saying this first one now must be 0. But then after that we have any, and any. I didn't put any other limitations. I just said the first digit has to be a 0. Well, how many ways can you pick 0 to be your first digit? The answer is only one way you pick 0. But then for digit 2, you can pick anything, so it's 10. For digit 3 is also 10, and digit 4 is also 10. So we have 1 times 10 times 10 times 10, or 10 to the 3rd, which is 1,000 ways to choose a pin that has a leading 0. So a little bit different. Not terrible though. And I said if a pin number is assigned at random, what is the probability that it has a leading 0? Well, we have to think about it this way. We have the probability here. There we go. So the probability of our event happening is the number of ways the event can happen divided by the number of possibilities in our sample space. So how many ways can we pick a pin number that has a leading 0? Well, we just found it. It's right here, 1,000 ways. We have 1,000 ways to do that. And out of all of our pin numbers, which we set up here, all of the possible pin numbers are 10,000. So we have 1,000 over 10,000, which is the same as 1 in 10. Right? That is our answer. We have a 1 in 10 chance, if we randomly chose a pin number, of it having a leading 0. If we wanted to extend this idea a little bit further in a slightly different way, we could think of each digit as being the number of ways that digit could be chosen divided by the number of possibilities for each digit. So we could think of it as our probability of our big event being the probability of choosing digit 1 times the probability of digit 2 times the probability of digit 3 and times the probability of digit 4. And the way that would work would be number of ways to choose digit 1 out of number of ways to choose all your digits. And same for second digit over all of them, third digit over all digits, and fourth digit over all number of all the digits possible. So the only way to choose a 0 is one way out of the 10 possible. And we have 10 ways to choose the second out of 10 digits, times 10 ways to choose the third out of 10, times 10 ways to choose the fourth out of 10. And all of those 10 over 10s are just 1, so we still get 1 over 10. So there are usually multiple ways you can consider pretty much every probability problem that we're going to look at. So we may find that come up again here in a moment. So if we look at D, it says if a PIN number is assigned at random, what is the probability that it ends with an even digit? So this is going to be interesting. We've got 4 digits still. And now we're saying that the first digit could be anything, right? Any number here, any single number here, and here. But this last one has to be even. So we have to remember that even is 0, 2, 4, 6, or 8. So we only have 5 ways to choose that last digit, but we still have 10 ways to choose all of our other digits. So we end up here with 10 times 10 times 10 times 5, which is 5,000 ways to choose this PIN. So the number or the probability here of our event would be the number of ways our event can occur out of the total number of events in our sample space. So we got 5,000 ways out of our sample space, which is still 10,000 possible pins. So 5,000 out of 10,000 is 1 in 2. That's 1/2. Right? So 1 in 2 chance. And again, the other way you could have thought about this was the 10 out of 10 times 10 out of 10 times 10 out of 10 times 5 out of 10. So that again would work the same way. Our probability of our event there would be 10 out of 10 times 10 out of 10 times 10 out of 10 times 5 out of 10, and you still would have gotten 1/2. In the same way that we would have found it above. Part E says, if a PIN number is assigned at random, what is the probability that it has no repeated digits? This is really a sort of classic combinatorics problem. It's kind of cool. So let's think about it. We have 4 digits still. How many ways can I pick that first digit? The answer is still any way. So we still have 10 ways to choose that first digit. But things get a little different because for the second one, we have lost one option. By the time we get to the third one, we have lost 2 options. And by the time we get to the last one, we have lost 3 options because we can't repeat numbers. So we have 10 ways to choose the first, but once we use that number, it gets removed from what's possible, so we're now down to 9. Whatever number we get there is removed. Now we're down to 8 possibilities for the third number. Take one more away, and we only have 7 for the fourth digit. So this is 10 times 9 times 8 times 7, which is 5,040 ways for that to happen. And the probability of this happening would be the number of ways it can happen, which we just found, over the number of all possible outcomes in our sample space. So we have 5,040 over our 10,000, which is 0.504. So I haven't really been doing decimals for the other ones just yet because they were all pretty common fractions. We could have said for each of these that, like, this one was 0.5. We could have done, the 1 out of 10 was 0.1. It's the same thing. If we wanted to look at this one by doing our probability of our event, doing our number of possible ways of the event happening over the sample space for each digit separately again, so it would be 10 out of 10 ways times 9 out of 10 ways times 8 out of 10 and 7 out of 10. So that is our probability for each one, right? And that would still give us the same thing as above. That's still 5,040 over 10,000, which is still 0.504. So it doesn't really change our outcome. And it doesn't matter to me which approach you take here for these problems. You could do the 50/40 over 10,000 by doing 10 times 9 times 8 times 7 and dividing it by 10 times 10 times 10 times 10, or you can do them all separately. In the end, they are exactly the same thing. So it doesn't matter to me which approach you take with these guys, either the red one or the purple one. So F says if a pin number is assigned at random, what is the probability that it ends with an even digit and has no repeated digits? So this one's going to be fun because here our event is that we have the probability that we have an even last digit and, so multiplied, no repetition. Well, luckily, we already know each of those probabilities. The probability that it has an even last digit we already found was 1/2. And then we just found that the probability of having no repetition was 0.504. Which means once we multiply 0.5 times 0.504, our total probability of giving a pin that ends in an even last digit but also does not have repetition is 0.252, or just over a 1 in 4 chance. It's 25.2%. A direct result of some of the properties we were just looking at with our pin number example is something we call a permutation. A permutation of a set of objects is the number of ways that we can order the objects in a row where the order matters. It is vital to remember here that the order matters. So if we looked at tails, heads, and heads, tails, yes, they both only have 1 heads and 1 tails, but they're in a different order. So they are different permutations. We're going to learn later about combinations, and in that case, order will not matter. For now, order does matter. So we want to focus on looking at permutation. So what is the formula for permutation? So the permutation of our objects from a set, the complete set has n, and we're choosing our objects, is P of nr, is how we have it here, is n factorial over n minus r factorial. Back in chapter 5, we looked a little bit at n choose r, so that would be for combinations. This is a little different. This is the permutation. And I will say you can, yes, do this in your calculator. In your calculator, you can find permutation, and eventually you'll find combination, and you can find factorials. All of this is in a probability menu. How we get there is this way. You hit Math, Let me find my pen. There we go. Math. And then you do arrow to the right. It starts on math, then it goes over to number, to complex, and then one more time, and it says probability at the top. Okay. And then what will happen after that is you will see that number 2 is your permutation. And just as an aside, number 4, so you see number 2, by the way, is NPR. That's the same as saying P of N choose R. Number 4 is your factorial. So that's your factorial. So if you want to find it directly, you can find the factorial in that manner. I have not found a faster way to reach either of these. This is just the easiest way to get there. And when we learn about combinations later, I believe that's in the next video, then in that case, we're going to go in here in math, arrow over to probability, and it'll be number 3. So we're going to use multiple operations within this menu. So this is where having a TI 83 or 84 is going to be really important. You can also do this on some scientific calculators, or if you're really good with canceling fractions and multiplication and those sorts of things, you can do this without a calculator. So I will say the easiest way to do it is to do it with the calculator, but you don't have to. So I wanted to let you know about that. So let's try one of these problems. What do we even use permutations for? Well, example 9.2.4 says a club has 12 members made up of 5 freshmen and 7 sophomores. So 5 out of 12 are freshmen, 7 out of 12 are sophomores. How many ways could a president, secretary, and treasurer be elected? So in this case, it matters who gets picked because each time you have 12 ways to pick one of them, and then the other 2 each get removed by 1 because one person can't do both jobs. So it's the same idea as saying here if we had, let's see, we'll do it just like we did. First of all, we'll do it the way we did it with our PIN numbers. So we have, for the first position, we would have, let's say it's the president. We could have any of the 12. Then we have who is left and who is left again, because you can't serve in 2 capacities. So we would start out with 12. We would have 11 to choose for secretary and then only 10 to choose for treasurer, or whatever order we put them in, right? So the way that we could figure out how to do any of these choices would be to say here that it would be 12 times 11 times 10, which is 1,320 ways. Or we can use our permutation. We can say that this is the permutation of out of 12 people, I just need to choose 3. And if we plug this into our calculator, we also get 1320. So there are 2 ways. There is a faster way and a slower way, but both ways will get you there. Kind of reminds me of the Alice in Wonderland, all ways are the Queen's ways. This one has all kinds of ways. So how many times could a president, secretary, and treasurer be elected if all of the officers must be sophomores? Well, in that case, we only have 7 sophomores. So here, again, we would have 7, and then 6 would be left, and then 5 would be left. Right? So we would have any sophomores, and then we would have the sophomores that are left, and then we'd have the sophomores left after that. So 7 times 6 is 42, times 5, right? So 7 times 6 times 5, which is 210 ways. What happens if we plug it in as a permutation? Well, for a permutation, we would say that out of the 7 sophomores, we just need to choose 3. And we end up getting the same answer, 210 ways. So not terrible. Kind of interesting thinking about how you can apply this to things in your life. For the next one, for part C, it says, how many ways could a president, secretary, and treasurer be elected if the president and treasurer must be sophomores and the secretary must be a freshman? Well, let's start with the first things first. So we have sophomores being president and treasurer, so sophomores. So we'll start there. So that would be a permutation of that. Out of the 7 sophomores, 2 of our officials have to be sophomores. And the secretary must be a freshman. We have 5 freshmen from which to choose just one. So we have a permutation of 7 choose 2 times a permutation of 5 choose 1. And our permutation of 7 choose 2 is 42. And our permutation of 5 choose 1 is just 5. So we end up again with 210 ways, which is interesting. And it only works out this way because of how many sophomores and how many choices we took away. Because if you think about it in terms of placement here, we have any sophomore, then we would have a sophomore that's left, and then for the last one we would have any freshman. Right? So we have 7 ways to choose a sophomore. Once that one's out of the pool, we have 6 ways to choose the next sophomore. And this is only by luck that there are 5 freshmen. If it had been 4 freshmen, it would have been 7 times 6 times 2. And this would have been over here, it would have been the permutation of 4, choose 1. Just so happened that I also picked 5, and that's how we ended up with 7 times 6 times 5, or 210 ways. So again, a couple different ways to do this problem. Let's see if we can figure out this last one. How many ways could a president, secretary, and treasurer be elected if the president must be a sophomore and the other 2 are freshmen? So this is a little bit different from the last one because we would say that if the president has to be a sophomore, so out of the sophomores, we have to choose 1. And out of the freshmen, which we had 5, we have to choose 2 for the other 2 positions. Well, the permutation of 7 choose 1 is just 7. The permutation of 5 choose 2 is 20, so we get 140 ways. So how does this compare to doing it sort of what we call the brute force way? Would be, well, let's think about our different positions. We have, for the first one, it has to be any sophomore. And then the other one, the second one would be any freshman. Right? So any freshman. And then we would have any freshman left. So how many sophomores do we have? 7. How many freshmen do we have? 5. But once 1 is taken out, then we only have 4. In other words, we end up with 7 times 5 times 4, which is 7 times 20, which we just found out is 140 ways. So again, whether we use permutations or we use sort of brute force, we're going to get to the same answer. I did want to go back and show you that you could have used the formula for all of these problems where we used a permutation. So if we did a permutation of 12 choose 3, if we use the formula, we would have P of 12 choose 3 being n, which is 12, factorial, over 12 minus 3, n minus r, factorial. Or 12 times 11 times 10 times 9, factorial. We can pull out just the 12, 11, and 10, because then 12 minus 3 is 9 factorial, and then we can cancel those factorials. So we end up with 12 times 11 times 10, which we already found out was 1,320 ways. In the same manner, we can do 7 choose 3 down here. So our probability of 7 choose 3 would be 7 factorial over 7 minus 3 factorial. So 7 times 6 times 5 times 4 factorial over 4 factorial. And again, the factorials cancel out. So we get 7 times 6 times 5, which is our 210. So this is what I was saying. If you don't have a TI 83 or 84 or a scientific calculator that can do combinations of permutations, you will be okay. You can do all of these using the formula or just using the brute force method. So the same thing could be said for all of the rest of these. For example, 9.2.5, I'm asking you to use permutations to answer the following questions. A says, how many ways can the letters in Columbia be arranged? Well, if you count them up, there are 8 letters in the word Columbia. So there are 8 letters. So the way that we can arrange them is the permutation of 8, choose 8, which is 8 factorial. And no, I did not multiply all that out. So you certainly can if you would like to. It's going to be a fairly large number. I just left it at 8 factorial. Now, if we wanted to do it with brute force, we could say there are 8 ways to choose the first letter, and then the 7 for the 7, then 6, then 5, then 4, then 3, then 2, then only one way to choose the last letter if we wanted to rearrange them. So that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 8 factorial. So sort of our brute force over here, 2, 3, 4, 5, 6, 7, and 8. We had 8 ways to choose the first letter. It means we have 7 left, then 6, then 5, then 4, then 3, then 2, and then lastly 1. And that would be our 8 factorial. So that's our sort of brute force way. And again, I'm trying to convince you to use the permutations on this problem. So B says, how many ways can the letters in Columbia be arranged if the first letter must be a vowel? Well, we better figure out how many vowels are in Columbia. Let's see here. C-O, L-U, M-B, I, and A. So there are 4 vowels in Columbia. So there are 4 vowels. And so the way we're going to think about it is, in this case, we still have our 8, 6, 7, and 8. Now we only have the vowels. It has to be vowel here, which are O, U, I, and A. So there are only 4 ways to choose that first letter. If we did this with permutations, that is the permutation of out of our 4 vowels, we choose 1. And that means then out of the other 7 letters, we just choose the 7 letters. Right? We only picked 1 for the first letter. So this P of 4 choose 1 this is our choosing 1 vowel for the first letter. And the remaining 7, this would be placing the remaining 7 letters. Okay? Because once we pull out just that 1 vowel, we only have 7 letters left. So when we use our permutations either by doing the calculator command or by doing it by hand, we end up with 4 choose 1 is 4. Our permutation of 4 choose 1 is 4. And permutation of 7 choose 7 is 7 factorial. And if we did it again, if we talked about doing this with a brute force method, once we chose our first letter, which has to be a vowel, there are only 4 ways to choose it. Now I've eliminated one of our 8 letters, so I only have 7 left, then 6, 5, 4, 3, 2, and only 1 letter for that last one, which is 4 times 7 factorial. So it works even using our brute force method. So please be aware that if I were to put a problem on the exam or on a homework that says use permutations to do this, then I want to see not the brute force method on the right, but I want to see the permutation computations on the left. I want to see the permutation of 4 choose 1 times the permutation of 7 choose 7. That's what I'm looking for. So when we start looking now at part C, which is a little different yet, a little bit more complicated. Whoops, I have 2 C's in there. So this is our first, we'll call this our first C. The next one will actually be a D. Sorry for that typo. So for our first C here, we said how many ways can the letters in Columbia be arranged if the first and last letters must be vowels? So thinking about it this way, that first letter has to be a vowel, right? So that's 4 choose 1 ways to choose the first vowel, right? So we're going to choose the first vowel. And we also need to choose the last vowel. Well, now we've already taken from our 4 vowels, we've removed 1. So we only have 3 vowels left to choose the last letter. So it may seem a little weird that we're choosing the first and last letters before we do everything else, but that's probably the easiest way to explain the method of finding all of these these permutations. So here we're going to place everything we know how to place that we're required to place, and then we'll place everything else. That's how our method works. So here we're going to place or choose the vowel at the end. So we chose our vowel at the beginning, and then we chose our vowel at the end. And now, out of our 8 letters, we have used 2 of them. So now we have to place the remaining letters, which are 6 of them, and we have to choose all 6 of them to place. So we're going to place the remaining letters. There we are, remaining letters. So when we do this, P of 4 choose 1 is 4. P of 3 choose 1 is 3, and P of 6 choose 6 is 6 factorial. So we end up with 12 times 6 factorial. And again, these are fairly large numbers. You are welcome to plug them into your calculator if you want, or you can just leave them as is. So if we think about it with our brute force method, 1, 2, 3, 4, 5, 6, 7, 8. Let's place our letters. Let's place our vowel, right? Our first one has to be a vowel. That's vowel number 1. And there are 4 ways to choose that one. Once I remove that one vowel, and now I want to place vowel number 2, then I only have 3 ways to choose that vowel because I already removed one. Well, now I have to place the rest of the letters, right? So now for these guys, we have to place the remaining letters. So that would mean I've used 2 already. I have 6 then, 5, 4, 3, 2, and 1. And again, that's our brute force method that if I were to tell you you had to use permutation to solve this problem, you wouldn't be able to use brute force here. Okay? But I want to show you why it works that way. And for part D, it says how many ways can the letters in Columbia be arranged so that B and L must remain together in order. Well, this is kind of cool because the way that we can simplify this, it sounds very complicated, but you notice I didn't leave much space. That's because now we consider B and L together as one letter. So now we're really only having to place 7 letters. So we think about it, 1, 2, 3, 4, 5, 6, and 7. We'll first place the BL. How many ways can we place BL together? Well, it has to be just one way, right? So we'll talk about placing BL first, right? So here, this is our place BL. And there's really only one way to place B and L together. Keep them together, right? And then what we have left is we have to place the remaining letters. Notice that we don't have 7 left anymore because we put B and L together. Now we only have 6 spaces remaining. So we'd have 6 times 5 times 4 times 3 times 2 times 1. Or here we get 1 times 6 factorial. So we get 6 factorial. So that's our brute force method. How does this work with permutations? Well, we say do the permutation of, think of BL as one letter, and we're going to place it, times the permutation of the remaining 6 letters that we need to place. So we get 1 factorial times 6 factorial, and 1 factorial is just 1. So we end up with just 6 factorial, just like when we did the brute force method. Our last example from this section says prove that for every integer n greater than or equal to 2, the permutation of n plus 1, choose 3, is n cubed minus n. So just when you thought you weren't doing more proofs, I bring you right back. So our statement here says that for all n in the set of integers, if n is greater than or equal to 2, then the permutation of n plus 1, choose 3, is equal to n cubed minus n. All right, our proof says we're going to suppose n is an integer such that n is greater than or equal to 2. And by the definition of permutation, we can say then that P of n plus 1, choose 3, is going to be n plus 1 factorial over n plus 1 minus 3 factorial. So we end up with n plus 1 factorial over n minus 2 factorial. So if we think about all these values that go into this, this is 1 times 2 times 3 times all the way up to n minus 3 times n minus 2, n minus 1, n plus 1. And our denominator would be 1 times 2 times 3 times all the way up to n minus 3 and then n minus 2. So what happens here is we can cancel out all of the terms leading up into n minus 2. And what we're left with then is n minus 1 times n plus 1, which is indeed n cubed minus n, as was to be shown. And I will say, don't worry too much about one of these short little proofs. I tend to not put those on the exam. So you may see a short one on homework, you may not. This is more of a fun exercise to show that you can use permutations even on problems where you don't necessarily know how big your sample set is.